Okay, the first thing we're going to do is go to desmos.com. If you haven't done this yet, I would really recommend you try this on your own time as well. And then we'll type in y equals ax squared plus bx plus c. And then Desmos won't do anything because it doesn't know what a, b, and c are. But you can add a slider for a, b, and c if you click the all button. So click. What I would like you to do is spend a little bit of time seeing what happens to the graph if you just change these numbers. C, for example, is the y-intercept. So if you raise or lower the y-intercept, it's just going to move the shape up and down the graph, and that's the only thing it changes. A is the leading coefficient, right? So if A is a large number, this is going to be a skinny little graph, and if A is closer to 0, it's going to be wider. If A goes negative, it changes the direction. So positive A means it's facing up. And if it's negative A, suddenly it's facing down. And these are the kind of things you can learn if you just go on Desmos and mess around for a little bit. But again, notice the leading coefficient determines the direction, whether you're up or down. And it determines the width, whether this is a wide parabola or a skinny parabola. That's what I mean by direction. So positive is up, negative is down. The shape generated by any quadratic function is called a parabola. So every shape we just saw, no matter what the coefficients are, we call that a parabola. Every parabola has a point that's either a minimum or a maximum. And that point, whether it's a minimum or a maximum, is also called a vertex. So I'll show you. This point right here is a maximum because I'm facing down. If A is negative, this faces down, and this is a maximum. But that point is also called the vertex. And on Desmos, if you've got one typed in, you can just mouse over the vertex and you can see the coordinates. X coordinate, comma, Y coordinate for your vertex. And then also, if it's facing up, the vertex is the minimum point on your graph. Parabolas have bilateral symmetry. Bilateral symmetry means there is just a line of symmetry. A lot of things have bilateral symmetry, like a butterfly has bilateral symmetry. A smiley face has bilateral symmetry. It just means you can draw a line through it and it looks like a mirror image of itself. When we draw this vertical line, we call that line the axis of symmetry. So you'll see that word later. Again, if you want to see the axis of symmetry, you can plot that as well. Make it easier to see. Here's my parabola, and notice no matter what I choose for my coefficients, the parabola always has that bilateral symmetry. I can always slice it with a vertical line. So now let's graph this function by generating a table of values. Table of values means x, y. We'll pick some numbers. And then to get the corresponding y values, I'm going to use the function y equals x squared. And so my numbers are going to be 9, 4, 1, 0, 1, 4, 9. This gives me a list of 7 points that I can put down on my graph using the x coordinate and y coordinate. And then we're just going to connect these dots to graph the curve. And remember, for any graphing question, you can always do this. Any graphing question, you can always just make a list of x values, calculate the corresponding y values, plot the points, and connect the dots. That's like the easiest way, that's the scrappy way of graphing a function. We're going to talk about another way to graph a function that's a little bit more robust, but also a little bit more difficult. If you forget how to do it the right way, you can always just make a table of values. So the next question says, let's begin with the graph I just drew. And I'm trying my best, but that one's, the right arm's a little bit wiggly on that parabola. Try again. So we're going to begin with the function y equals x squared. And now we're going to graph and write another function that has the same shape, but translated 2 units to the right and 4 units down. The way I'm going to do a question like this is I'm going to put those dots down that intersect with the grid lines really nicely. Actually, it's supposed to be 3, 9. Right, so these are the points that I plotted from before when I did the function y equals x squared. But this time I'm going to translate all of these points 2 units to the right and then 4 units down on my graph paper. And so this moves here, this point moves here, this point is going to want to move right there, this point moves down to the origin, and this point moves right here. So now I've got a new set of 7 points, and I just have to connect these dots and get another parabola that's the same shape as the blue one. I just moved it 2 units to the right and 4 units down. That is the first half of this question. It says graph it. The second half says write down what the function is, and this is how I'm going to do that. Where I have the x in my original function, I'm going to replace that with x minus 2. And then at the end, I'm going to subtract 4. What these are doing is the -2, that's going to move it 2 units to the right. And the -4, that's going to move it 4 units down. Okay. What if I wanted to move the blue curve 1 unit to the left? Yeah, inside the parentheses, I'll do x plus 1 to move it 1 unit to the left. So inside the parentheses, positive means move it to the left, negative means move it to the right. What if I wanted to take that blue curve and I wanted to move it 5 units up? Yeah, at the end of the equation there, I would add plus 5 instead of -4. Adding to the end moves it up. Subtracting from the end moves it down. But you keep the same shape because you still have the parentheses something squared. You know, if you wanted to see this, it's easy to do on Desmos as well. You just say, let me subtract something. Oh, I need to square it. There we go. If I subtract something inside the parentheses, that's going to move it farther to the right. And if I add something or subtract a negative, that moves it to the left. And if I add something positive, it moves it up. If I add something negative or subtract from the end of the function, it's going to move it down. Questions about how you do this question? All right. Now, every polynomial, well, let me say that again. Every quadratic polynomial can be represented in vertex form. This is called vertex form. And if I was talking about a quadratic function, I would write y equals, and then I would write my polynomial. It looks like a times parentheses x minus h squared plus k. X is the variable, a is the leading coefficient. That is the same a as in factored form, and it's the same a as in expanded form. H, this time, is going to be the x coordinate of the vertex, and k, as it shows up here, is going to be the y coordinate of the vertex. The reason that works is because if you just have the y equals x squared function, your vertex starts off at 0, 0. And then if you want to move that vertex around, you subtract a number to move it right. You add a number to move it left. At the very end of the equation, you add a number to move the vertex up, and you subtract a number to move it down. That's how we ended up with this vertex form. We call it vertex form because it's so easy to see what the coordinates of the vertex are just by looking at it. Like in this top left example down here, what is the leading coefficient? 3. What is the coordinates of the vertex? 2 and 5. Yeah, we expect to see x minus the x coordinate of the vertex. So make sure you know the vertex here is positive 2, 5. What about this one? Leading coefficient is 1, and the vertex is at -1, -1. Down here, the leading coefficient is 2, and the vertex is at
0.
Very good. This is a tricky question. But if this were in vertex form, and the x coordinate of the vertex is 0, well then you don't have to write -0, and you don't need the parentheses either. So you just write it like 2x squared minus 1. You might also notice that this is both the vertex form, but also the expanded form. In other words, this polynomial has a distinct expanded form and factored form, but the vertex form is actually just the same thing as the expanded form. And that's because the x coordinate of the vertex is 0. That's when this happens. Okay. Last one down here. What is the leading coefficient? -1. What is the vertex? -4, 0. Again, because if I was writing this in vertex form, I write -1 x minus -4 squared plus 0. But 2 negatives make a positive, and I don't have to write plus 0 on the end. And so again, you might say, yeah, this is in vertex form, but it's also in factored form at the same time, right? And in the case where the y-coordinate of your vertex is 0, you're going to get the same factor in vertex form. If the y-coordinate is 0, that means your function has only one place where y is equal to 0. So there's only one root that's just repeated twice. And so you expect to see the same factor squared whenever you put it into factored form. And that's also coincidentally the vertex form. Does that make sense? Questions? Okay. Here we go. The following quadratic function is given in vertex form. If I want to rewrite this in expanded form, this is what I would do. I would take the part that says parentheses x plus 5 over 2 squared, and I'm going to go ahead and square it. Meaning, I'm going to go ahead and multiply x plus 5 over 2 times x plus 5 over 2. And in the bottom right corner, that's 25 over 4. Whenever I multiply 5 over 2 times 5 over 2. And now I'm ready to write down 2 times x squared plus 5x plus 25 over 4 minus 7 over 2. I just did the squared part, but I haven't multiplied by 2 yet, and I haven't subtracted 7 halves yet. Now I'm going to distribute the 2. 25 over 4 times 2 is just 25 over 2. And then the last thing that must be done, 25 minus 7 is 18 over 2 is 9. And that is expanded form. We started in vertex form, and now we found expanded form. Questions?
Where'd you get the 5x?
Yeah, where'd you get the 5x from?
Right here? So I'm trying to add together this plus this. Right, I've got 5 halves x plus 5 halves x. And that gives me 2 copies of 5 halves x, and then the 2's cancel, just 5x. Good question. Other questions? Okay. Now, the next thing I've got typed up here in my notes says, how do you find the vertex coordinates if I give you the function in expanded form? This is not super straightforward, but we'll talk about it. The x-coordinate of the vertex, so when I say x-coordinate of the vertex, I'm talking about h. That is just the midpoint of the 2 roots. What I mean by the midpoint is it's halfway between the roots. And you can find that by averaging them. Just root 1 plus root 2 divided by 2. That's going to give you the x-coordinate of the vertex. The reason that happens every single time is because I could write down any old quadratic function, and I could draw the axis of symmetry here And you'll notice the axis of symmetry always passes through the vertex. And since this parabola has bilateral symmetry, the axis of symmetry is halfway between the roots. I don't know if I said this, but the roots are the x-intercepts. So the roots are the places where this purple curve passes through the x-axis. And the x-coordinate of the vertex is right here. It's going to be halfway between the roots every time. So, if I know that the x-coordinate of the vertex is the midpoint between the roots, that really helps me if I know what the roots are. But if the function is given in an expanded form, I don't know what the roots are, right? I only know a, b, and c. So we can work on this a little bit and make it easier for you. We'll say R1 is the root I get by taking negative b over 2a plus the square root of b squared minus 4ac over 2a. And then R2 is going to be the other root, which is b squared minus 4ac all over 2a. The difference is I did plus on one side and minus on the other. So let's say those are the definitions of my roots. And now I want to calculate h, which is the first root plus the second root divided by 2. Okay, so I'm going to add together these roots. But when I take the first root plus the second root in the numerator, do you see anything that cancels? The what? That's not going to cancel each other out. What I'm thinking about when I say cancel is I've got plus all of this ugly junk, and then I also have minus all of that same stuff, right? So the positive version and the negative version are going to annihilate each other. What do I have left? I've got that negative b over 2a plus another copy of negative b over 2a. That's like having 2 copies of negative b over 2a. But then this 2 in the numerator and that 2 in the denominator, they're going to cancel each other out. And so in the end, when I'm done simplifying, h is equal to negative b over 2a. That's a formula worth memorizing. It's also the first term in the quadratic formula. So if you've already memorized the quadratic formula, that should be easier to remember. But this is how I find the x-coordinate of the vertex if my function is in expanded form. And then the next part of this says the y-coordinate can be found by just plugging in the x-coordinate. Okay? There's no special formula for the y-coordinate. You just plug in the x-coordinate. I'll show you what that looks like. We'll work another example here. The following quadratic formula is function. Is given in expanded form. We want to rewrite it in vertex form. So here we go. We've got x squared plus 2x minus 5. And what I would like in the end is a times x minus h squared plus k. That's my vertex form. What is a? 1? And that's good. So I already know part of my vertex form. I already know this is going to be 1 times x minus whatever h is squared plus k. But I need to know h. I can find h because h is just negative b over 2a. What's b? 2. So negative 2 over 2 times 1. So negative 1. And if h is -1, I would write x plus 1 for my answer right here. And if I want to find k, I'm just going to start from my original equation here and then plug in the x coordinate of my vertex. And I just found the x coordinate of my vertex. That is -1, and so that's 1 minus 2 minus 5. K is -6. And then down here, when I add k, I just say -6. This question is going to be on your test Monday. Any questions about how to do it? You got the A already given to you. You've got a nice neat formula for h, and you find k by plugging in h into your original function. Okay, the following quadratic function is given in vertex form. Now I want to rewrite this in factored form. So ideally, when I'm done, I would write a times x minus r1 times x minus r2. What is a? Yeah, it's just 5. I can see that when I'm looking at vertex form. Now, how do I find my roots? To find the roots, we set y equals 0 and solve for x. Remember, the roots of your polynomial are the zeros of your function. And what a 0 means is you set the y value equal to 0 and you find what are the x values that make y equal to 0. So I'm going to rewrite this function as the equation 0 equals 5 times x plus 1 squared minus 80. And then we solve for x. So I add 80 to both sides. And then I divide both sides by 5. And now what do I do? Take the square root of both sides. And when I take the square root of both sides, yeah, you have two solutions. You have to throw in a little plus or minus sign. The last step to solve for x here, subtract 1 from both sides. Very good. And that gives me two solutions. And those solutions, those are my roots. So I'm ready to write my answer. The answer is 5 times x minus 3 times x plus 5.
Are the same as the zeros, right? The roots are the same as the zeros?
Yes, the roots and the zeros are the same. So really quickly, what we said is I want to rewrite this in factored form. To write it in factored form, I have to know what is a and what are the two roots. A is easy because a shows up in the vertex form that you're given, so we knew a is 5. And then to find the roots, we set y equal to 0 and we solve for x, and those two solutions we get are also the roots that go into the factored form. Questions? No? Okay. How do you find the vertex coordinates? If the quadratic function is in factored form, Well, if it's in factored form, the cool part is we already know what the roots are. In factored form, you can see the roots. And so when I say the x coordinate of the vertex is the midpoint between the two roots, you just find the midpoint between the two roots. Once again, there's no fancy formula for the y coordinate. You just have to plug in to your original function to get the y coordinate. You plug in the x coordinate into the original function. Here's an example. I've got a function given in factored form. Now I want to rewrite it in vertex form. So at the end of the day, I would like to write a times x minus h squared plus k. What is a? 3. So that's good. I can already write that much. To get h, which is the next thing I need, I take r1 plus r2 divided by 2, which is going to be
1/3 plus 1 over 2.
very good. So that's 4/3 over 2, which is 2/3. And the last thing I need to do is find k. There's not a special formula for k. You just take your original function and you plug in x equals h, and then that makes y equal to your y coordinate of the vertex. And then this is 3 times 2/3 minus 1/3, which is 1/3. And then 2/3 minus 1 is negative 1/3. So this is going to be a negative number because there's one minus, and it's going to be 3 divided by 9, or 1/3. Any questions about how we did this? Okay. So, every quadratic polynomial can be written in expanded form. Every quadratic polynomial can be written in factored form. And every quadratic polynomial can be written in vertex form. So the first thing we learned on Monday this week was how to take a factored form quadratic and expand it so that we would have the expanded form. And then what we spent working on the rest of the class was how do you take an expanded form quadratic polynomial and then factor it. So that was Monday. Today, we have expanded a vertex form quadratic. We've also taken an expanded form and rewritten it into vertex form. And then we took a vertex form quadratic and wrote the factored form, and then the last example that we just worked, we took a factored form and rewrote it as vertex form. So let's count how many different questions I could write. There are 6 different questions that I could ask you just about taking a polynomial and rewriting it in a different form. And all 6 of those questions are going to be on your test, right? They're like 20, maybe 25 questions on your test Monday, but that's going to be 6 of them right there. Now I'm going to tell you a little story that I heard. There's a brilliant mathematician, his name was David Hilbert, and he lived, I think he was about 45 years old around the year 1900. And Hilbert was famous for doing a bunch of math proofs with infinities. Like he proved that there's many different types of infinities, and some infinities are bigger than other infinities. But the story goes that math professor David Hilbert was sitting down at the university lounge with an English professor and a philosophy professor. And the philosophy professor is always eager to find out what is the essence of a topic, or what's the substance of some kind of concept, right? Very philosophical. So he says to an English professor, "What is poetry?" And the English professor says, "Well, poetry is the art of giving the same object different names. A good poet knows that there's many ways to describe the same thing, and you choose the best description to fit the context of the poem." And the philosopher says, "Wow, that's a really great response. I never thought of poetry that way." And then the philosophy professor turned to the math professor and he says, "What is mathematics?" And the math professor says, "Well, mathematics is the art of giving the same object different names. A good mathematician knows there's many ways to describe the same thing, and you choose the best description to fit whatever context you're working in." Right? That's the joke. It's the same as poetry. A quadratic polynomial is not any one of these three things. These are just three different kind of names that we give to the quadratic polynomial, and they could be more or less useful depending on the situation, right? Depending on what you're trying to find. If you happen to want to know the y-intercept, expanded form is the easiest because you can see the y-intercept. If you want to know the location of the vertex, vertex form is the most useful because you can just see the vertex. If you want to know where the roots are, then factored form is the most useful because you can see the roots. And that's why it's useful to be able to switch between those. New vocab word is the word multiplicity. I'll write it out for you. It is multiplicity. And this is the way that multiplicity works. If I look at this polynomial, I can see that it factors like x minus 3 squared. So the root of this polynomial is positive 3, but the multiplicity of this root is 2. And I say the multiplicity is 2 because the corresponding factor to the root positive 3 looks like parentheses x minus 3. And this shows up 2 times in my polynomial. So that little exponent 2 is telling you the multiplicity of the corresponding root is 2. What about this one? I can look at this quadratic and I can tell that this factors as x minus 5 and x plus 2. So there are 2 roots here, 5 and negative 2. And the multiplicity of each root is just 1, because I could imagine little 1s there. So the little power on the corresponding factor is just 1. Each corresponding factor only shows up once. Right now, when we talk about quadratics, we're only seeing 2 factors show up in the factored form. So these are the only 2 cases you could have. But starting next Wednesday, we're going to talk about polynomials that have more than 2 factors, and we'll have more discussions about what multiplicity means. But like I said before, if a root has multiplicity 2, then it's one of those cases where the factored form and the vertex form are actually the same. So like this is factored form, but it's also, you'll notice, the vertex form. It's just that the vertex appears at what coordinates?
HK.
Yeah. If this is the vertex form, what's the vertex coordinates? I think I heard 3, 0. Yeah. So if the vertex is sitting on the x-axis, the y-coordinate of the vertex is going to be 0, and there's only going to be one place where y equals 0. So it's just one root with multiplicity 2. So consider the function provided below. Find its vertex. Find its roots. Find its y-intercept. And then we'll draw the axis of symmetry, and then we'll graph the function. So I'm going to skip vertex for right now, because I don't know the vertex. This is expanded form. I can't see what the vertex is. We'll save it. If I want to find the roots, I need to rewrite this in factored form. How does this factor? Very good. I can write x minus 3 times x plus 1. So then my roots are 3 and negative 1. Do you remember how to find the x-coordinate of my vertex? It's the midpoint between the roots. What's halfway between 3 and negative 1? 1. And then to find k, I just have to start from my original function and plug in x equals 1, right? It's h squared minus 2 times h minus 3. But h is 1, so this is 1 minus 2 minus 3. So k is negative 4. Positive 1 minus 2 minus 3, negative 4. So my vertex happens at 1 comma negative 4. What's my y-intercept? Perfect. Remember the y-intercept, that's what happens when x is equal to 0. And when x is equal to 0, y is equal to negative 3. Any questions so far? Okay, so let's graph it. We're going to put the vertex at 1 comma negative 4. That point is 1, negative 4. That's going to be my vertex. We're going to put the roots down, and remember that roots are your x-intercepts, okay? These roots are telling you the location of your x-intercepts. So 3 and negative 1. Here's 3 as an x-intercept, and here's negative 1 as an x-intercept. And then the last thing I know is my y-intercept is at negative 3. So let's plot my y-intercept at negative 3. I also had the instruction that I should draw my axis of symmetry. So maybe I'll just put down my axis of symmetry. Remember, your axis of symmetry is just a vertical line that passes through the vertex. So if you found your vertex, just draw a vertical line through that vertex and you've got your axis of symmetry. I can actually make one more point before I start connecting the dots. And I'm going to put my extra bonus point right here. And I decided to put it right there because if I look at my y-intercept and then I use my axis of symmetry, I'm placing another point at the same position vertically, at the same distance away from my axis of symmetry. So it's kind of like the mirror image of the y-intercept. And every time you should have 5 points that you can graph with. You've got 2 roots, which give you your 2 x-intercepts. You've got 1 vertex that you can plot. You've got 1 y-intercept, and then you've got 1 mirror image of the y-intercept. And that's what we have here. Once you're done plotting these 5 points, then you're ready to connect the dots like this. And having these 5 points, it tells you what direction, like if you're pointed up or if your parabola points down. It tells you where the vertex is, and it tells you about how wide or how skinny your parabola should be. And then you can just extend it. That's good enough for this class, okay? Are there any questions about how you graph this? So what if you had a graph like this? If this were my example, I would be able to find the vertex, right? And plot the vertex point first. I would be able to find the y-intercept. And after finding the y-intercept, I could draw the axis of symmetry. And I could put another point down over here. That's the same vertical, but the same distance away from the axis of symmetry. But that's only 3 points. The reason there's only 3 points is because there is no x-intercept, right? This is going up, and it's away from the x-axis. So it never crosses the x-axis. And that means I don't have any roots to plot because these roots are complex numbers. I can only put the x-intercepts down if they happen to be real numbers, right? My x-axis only has real numbers on the x-axis. If you end up with complex numbers for your roots, like on Monday when we were using the quadratic formula, what if the radicand part of the quadratic formula was negative? You can't take the square root of a negative, well, you can take the square root of a negative number, it's just imaginary. And if that's the case, you've got roots that are complex numbers, they don't show up here. And in that case, the best you can do is plot these 3 points and connect the dots and extend it, draw the best you can. Okay? Just be aware that that might happen, and that's okay. You can still draw those 3 points and plot it. Let's do one where we start from vertex form. Notice vertex form here. And we're going to do the same thing. I'm going to find the vertex. I'm going to find the roots. I'm going to find the y-intercept. I'm going to find the axis of symmetry and then the symmetric point, and then I'll graph the function. I can tell what my vertex is by looking at it. What's my vertex? Perfect. -3 and +1. The roots, remember finding my roots? The roots means you set y equal to 0. And then if I set y equal to 0 and I solve this equation, then the x value are my roots. So I might even just replace x with r to remind myself I'm looking for my roots here. But again, we're setting y equal to 0 and then we're solving the equation. So, subtract 1 from both sides. They're both negative, so I can cancel out the negative. You can imagine multiplying both sides by -1 if you want to. And then take the square root of both sides. The square root of 1 is just 1, but since I took the square root of both sides, I have to throw in a little plus or minus sign. And lastly, I will subtract 3 from both sides. And I find that my roots take place at -2 and -4. The y-intercept, this happens, I get my y-intercept whenever x is equal to 0, okay? And if x is equal to 0, let me look back at my original equation and write -0 plus 3 squared plus 1. 3 squared is 9, so this is -9 plus 1, and my y-intercept is the point y equals -8. In the previous example, exercise 9, the y-intercept was easy to see because it was in expanded form. But this time I don't have the expanded form ready to go. The way I find it is I set x equal to 0, and then I simplify, find my y-intercept. Okay? Okay, I'm going to put down my y-intercept. I'm going to put down my roots. So -8 is my y-intercept. There it is. Remember, your roots are your x-intercepts. So my x-intercepts are at -2 and -4. Here's the root at -2, and here's the root at -4. My vertex was -3, 1. So the x-coordinate is -3, the y-coordinate is 1. And so now I've got my vertex, my roots, my y-intercept. I can go ahead and draw my axis of symmetry, because my axis of symmetry is just a vertical line that passes through my vertex. And then I get one bonus point. I'm going to put my bonus point right here. Do you see why? I look at my y-intercept. I put it on the same level vertically, but the same distance away from the axis of symmetry. So it's 3 units away. On the right side, it's going to be 3 units away on the left side. And now I graph by just connecting my dots. And that's going to be good enough for this problem on your test. So similar to the previous one, except this time we started with vertex form. Do you guys have any questions about how we did that? Okay. Let's see what we get next. Again, the exact same question, but this time we're starting from factored form. We want to know what is the vertex. We want to know what is the roots. We want to know what is the y-intercept. I can get my roots just by looking at it, because this is factored form. What are my roots?
1 and 5.
Perfect. Those are going to become my x-intercepts. My y-intercept, I can't see it because I don't have expanded form ready. But if I set x equal to 0, this becomes -1/2 times 0 minus 1 times 0 minus 5, which is going to be negative 5 over 2. The last thing I need is my vertex, and hopefully you remember that the x-coordinate of my vertex is halfway between my roots. So what's halfway between 1 and 5? 3. And then to get the y-coordinate of my vertex, I take my original function and I plug in the x-coordinate of my vertex. Of course, h is 3, so this is 3 minus 1, which is 2, and then 3 minus negative 5, which is negative 2. Two negatives make a positive, and I think k is 2. So when we go to graph this, we're going to put down all 5 points again. And my vertex is at 3, 2. So here's 3, 2 for my vertex. My roots are at 1, 5. What I meant by that is my roots are my x-intercepts, and one of them is at x equals 1. The other one is at x equals 5. Then I need my y-intercept, which is at negative 5 halves. In other words, a little bit past negative 2, negative 2.5. Right here, that's my y-intercept. I'm going to go ahead and draw my axis of symmetry. My axis of symmetry is a vertical line that passes through the vertex. And after I draw this axis of symmetry, I get a bonus point by taking my y-intercept and putting another point at the same location vertically and the same distance away from the axis of symmetry. Now I've got 5 points, and I can connect my dots like this. Are there any questions about how we did that one, starting from factored? If I ask you to complete a table of values using a graph, I think this kind of problem is easy. You just have to look for points on your graph where this curve intersects the grid lines really nicely. Like, I don't like that point, but I do like that point, just because the grid lines line up really good. The grid lines line up really nice here too, and also right here. The grid lines don't really line up very well again until right there and right there. And they don't really line up very good. Yeah, that's probably fine. That's good enough. And so looking at those points, that's how I find out my values in my little table. So here at that point, x is negative 3 and y is 0. At this point, x is negative 1 and y is 6. At this point, x is 1 and y is 8. That point gives me 3 and 6. And this point gives me 5 and 0. If the curve doesn't pass through both vertical and horizontal grid lines at the same time like that, then just don't worry about including that point in your table. Okay, that's good enough. And you can imagine for a moment that you could actually write this function down if you wanted to, because you know the coordinates of the vertex, right? And so if I start off with vertex form, this is x minus 1 squared plus 8. How do I find a? You know, you just have to pick another point. It doesn't really matter. But I'm going to take this point and plug this in for x and plug this in for y. And so my y is equal to 0, and then I get a times 5 minus 1 squared plus 8. Solve this equation for a. So I'll subtract 8 from both sides, and this is a times 4 squared. Divide both sides by 16, and a is negative 1/2. Do you know a? You come back here. Replace the a with negative 1/2, because we just found out what it is. Okay? So you can look at a graph now. You can look at a graph where there's a parabola, find the vertex, and then you can write this in vertex form. The only thing you don't know right away is the leading coefficient. But you can always find the leading coefficient if you take just any other point. I randomly chose that point, but you could choose any point on the parabola and then plug it in for x and y to solve for a. If I give you a table of values, you can look at it and write the quadratic function. The way I would do this is I would say, y is equal to 0 right here, and y is equal to 0 right here. That means my roots are what two values? Negative 2 and 1. So if I want to sit down and write this in factored form, I have to write a times x plus 2 times x minus 1. I still don't know what a is, but I can figure out what a is if I just choose any other point. It doesn't matter, just pick one. And plug in the y value at that point for y, and the x value at that point for x. And this orange point I selected has x equals 0, y equals negative 6. And then in this case, I get negative 6 equals a times 2 times negative 1. So divide both sides by negative 2. A equals 3. Go back, replace my a with a 3, and that's good enough. Once you have it in factored form, then you could choose to rewrite it in expanded form or vertex form or whatever. But if you're given a graph, I could have also said, well, one of my roots is at negative 3 and one of my roots is at positive 5. I could have written the factored form first and then tried to figure out what a is. Or you can look at the vertex coordinates here. I don't really know what my vertex is when I look at that table of values. And without knowing the vertex, the roots are the next best thing to try to work from. So here we go. This problem says, suppose a football is kicked from a hill that is 48 feet above a lake. And so I'm going to draw the picture. Here's my lake. And the surface of my lake should be almost exactly flat. But here's my football. And it's starting off 48 feet above the surface, and then we're going to kick it. So after it's kicked, it's going to travel up, and then it's going to travel down, and it's going to hit the lake. I'm actually given a function where y represents the vertical height of the football, and t represents the number of seconds after the ball is kicked. So if you tell me how long it's been since we kicked the ball, I can tell you the height of the ball according to that function. The first question says, when will the football reach its maximum height? Well, the maximum height happens at the vertex, right? So let's look at this polynomial and try to find the vertex. The x-coordinate of the vertex would be negative b over 2a. Remember that formula? So negative 32 divided by 2 times negative 16, that is 1. But this isn't giving me y as a function of x, it's actually giving me y as a function of t, right? And that means at the vertex, t is equal to 1, meaning I reach the maximum height 1 second after the ball is kicked, right? So I go vertex. That's the answer to the first question. The second question says, what is the maximum height that the football is going to reach? And to find that, I'm just going to plug in t equals 1 into my function, right? So negative 16 times 1 squared plus 32 times 1 plus 48. So the answer to the question is the maximum height the ball is going to reach is just 64 feet above the surface of the lake. In other words, this height is 64. The last question says, when will the football hit the lake? When it hits the lake, that means y is equal to 0. So again, let's go back to my original function here. But I'm going to set y equal to 0. And then if I solve for t, I will know what time it was when the ball hit the lake. So I'll divide both sides by negative 16. So t squared minus 2t minus 3. Like I said, I just divided by negative 16. 0 divided by negative 16 is still 0. And then I need to factor this. How does this factor? So I've got two solutions. Either t is equal to negative 1 or t is equal to 3. The two possibilities here are either the ball hits the lake 3 seconds after you kicked it, or the ball hits the lake 1 second before you kicked it. Which one makes sense?
3 seconds.
Right. Yeah, the negative 1 part doesn't really make sense in the context of my problem. So the answer to the question is 3 seconds after the kick. Let's suppose the following function gives the supply and demand relationship between the market price and number of goods produced for a new type of Pokemon card. So P is the price of a card. N is the number of cards that they produce and sell. And what this equation is telling us is if they only made one card, right? The Pokemon company only produces one of these Pokemon cards, then the price would be about $20, right? If it's that rare, people might be willing to pay $20 to get something that's one of a kind, you know? There's people who collect cards like this, and the more rare the card is, the more it's worth. But as they start to produce more and more of these cards, N starts to increase and P, the price, starts to decrease. So if they created a whole bunch of these cards, like they create like 20 million cards, then it's going to lose its value. People don't really care to collect something if there's 20 million copies of it. That's what it's trying to say there. The next part of the problem says the variable cost of manufacturing and distributing each card is 65 cents, and the fixed cost associated with the design and marketing are $40,000. The Pokemon Company wants to maximize profit. So let me give you a little equation that you would need to solve this question. Profit is going to be equal to revenue minus expenses. When I say revenue, I mean how much money is the company bringing in? Disregarding all of the costs for right now, but how much money are we bringing in? That would be the price of the card times the number of cards sold. That's how much money you're bringing in, okay? Minus the expenses, well, there's actually a lot of expenses. First of all, each one of the cards costs 65 cents to produce. So 65 cents times the number of cards, that's a cost associated with producing the cards. And then we also have the expense of design and marketing, so we also have to add in an extra $40,000 of expenses. And that gives me the total picture of my company, right? So again, profit is going to be P times N. I have a definition, though, that I can substitute in for that P variable. I can write 20 minus 0.001 N instead of writing P, minus 0.65 N minus 40,000. Okay, still simplifying, let me just call profit Y. And then if I distribute that N, it's going to be 20N minus 0.001 N squared minus 0.65 N minus 40,000. I'm going to go ahead and write this in the correct order for expanded form. So I'm going to write the N squared term first. And then I'll write the N term, which is 20 minus 65 cents. It would be 1935 minus 40,000. So it's a quadratic function. And the negative sign in the front for the leading coefficient tells me that this parabola, if I were to graph it, is facing down. And that means if my parabola is facing down, the vertex is a maximum point. Right? So the negative sign out front tells me I'm facing down, and that means the vertex is also the maximum. So to find my maximum profit, what I need to do is find the coordinates of my vertex. Now, the y-coordinate, or sorry, the x-coordinate, or I should say maybe the n-coordinate of my vertex, that's going to be negative b over 2a, which is negative 19.35 divided by negative 0.002. Two negatives make a positive, and this is going to be the number 19.35 over 0.002. If I wanted to mess with the decimals, move the decimals 3 places over to the right, this would be 19.350 divided by 2. you can use a calculator, right? On the second test, you can use just one specific type of calculator. You can use the TI-30X, Roman numeral 2S. This is the one you're allowed. So let's go ahead and plug in 19350 divided by 2, just so I don't have to work too hard. This is the number 96575. Okay. That is the n coordinate of the vertex. How do I find the y coordinate of my vertex? I just go back and I plug in this number into my equation, okay? So it's going to be negative 0.001 times 9675 squared plus 19.35 times 9675 minus 40,000. Again, everybody make sure you bring your calculator on Monday, because I don't have extras and you might want it for a question like this. Plus 19.35 times 9675 minus 40000. Aha. If you did this correctly, and assuming I did it correctly, which is a big assumption, that is the profit, right? That's the profit coordinate of my vertex. So let's see what the question was actually asking. How many cards should they produce? Well, if they want to produce the maximum profit as it happens at the vertex, they should produce 9,675 cards. What is the maximum possible profit? $53,605.63. Another question I could ask is, what is the market price? And to find the market price, you would use this, right? You'd do 20 minus 0.001 times 9675. And that is 10.33. Okay, so again, how many cards should they produce? About 9,000. If they were to make more cards, why would that reduce their profit? If they made and sold more cards, that's going to actually reduce their overall profit because their market price is decreasing. Collectors are willing to pay less money for the cards. And so they're selling them at a lower and lower price, but their fixed cost remains the same. Okay? The maximum possible profit was like $53,000, and the market price was $10.33. This is actually a question that people, in companies like that think about, right? If you're involved in any sort of company that kind of creates a collector's item, like if you work for the Beanie Baby company, for some of you that are 30 years and older in this classroom, Beanie Babies were a collectible that were like a huge hit in like 1995, right? People were going nuts. They would pay like $20, $30 for these like tiny stuffed animals. Some people would pay hundreds, thousands of dollars for these stuffed animals. But the idea was, if it was rare, if they didn't make a lot of them, then people would be willing to pay more for something that's rare. And if you make too many of them, then the price drops. So if you were working for one of these companies, this is actually a calculation you would sit down and do as a marketing person, as a business person, you're going to sit down and say, how do I maximize the profit of my company? Well, you have to choose how many you make. You don't want to make too many market price drops. In real life, the functions that describe the market price are not linear, right? They're like nonlinear curves. And so it's a little bit more complicated than this. Suppose you have 100 yards of fencing. Let's say you're like a rancher or something. And your goal here is that you want to enclose a rectangular area using your fencing. One side is going to be enclosed by a pre-existing wall. So you don't have to use any of your fence along the wall side. Okay? You get as much wall as you want to. But now we're going to find the dimensions of this rectangle, which means I'm going to find the length of the rectangle, the width of the rectangle. I may want to find the area of the rectangle that enclose the maximum area. So I want to make the biggest pen possible for my cows or my pigs or my goats or whatever, using only 100 yards of fencing. Think about this for a moment. What's the optimal shape for maximizing the area?
A rectangle?
Yes, and you know you have to make a rectangle according to the problem. We're going to enclose a rectangular area. But just like among the rectangles that you could choose from, how do you choose the most effective rectangle for maximizing area?
What do you mean by effective rectangle?
What I mean is you've got 100 yards of fencing, so should you put 5 yards here, 5 yards here, and 90 yards over here?
No,
Why not?
because it's going to look weird.
Just because it'll look weird?
Yeah, it's going to be really long and then the sides are going to be short.
Uh-huh. Yeah, it's make a super long rectangle with short little sides. Is that going to have as much area as if I did 80, 10, 10? The area here would be 10 times 80, which is 800, right? If I did 80, 10, and 10. But if I did 95 and 5, the area I can enclose is only 450 square yards. Okay. Does that make sense? So what if, I mean, it seems like it's getting better if I make these sides longer, right? What if I use only 10 yards here and I split the remainder 45, 45? Well, then my area I can enclose is only 450. So there's some kind of balance, right, between spending some fence on the length side and spending my fence on the width side. What's the right balance between length and width here to make it? Huh? Not 20 and 30? You're saying 30 for the length and 20 for the width? Then you've got some left over, right? You've only used 70 yards. So you can always make it bigger by adding the remainder to either length or width. Okay, okay. I'll cut to the chase here. Let's solve this problem. Rather than guessing and checking, let's say the area is the length times the width. And since I only have 100 yards, that means the length plus 2 times the width is equal to 100. In other words, the length is negative 2w plus 100. And I'm going to substitute that in here so that my area is given by negative 2w plus 100 times w. I'm going to distribute the w, and I get minus 2w squared plus 100w. This is a quadratic function. It's an expanded form. And if I want to maximize the area, I'm trying to maximize this function. Well, what would this look like if I were to graph this on a plane where I graph the width as my horizontal axis and the area as my vertical axis? The negative 2 in the front, that tells me that my parabola is facing down. In other words, it's going to look something like this. And that means my vertex is the maximum area that I can possibly get. So let's put this into vertex form, or at least we should calculate the vertex maybe. The x-coordinate of my vertex is negative b over 2a. So that's negative 100 over 2 times negative 2, which is 25. That's the width, right? If it's the x-coordinate of my vertex, that's actually the width here. And if that's my width, that side is 25. This side is the same because it's a rectangle, so 25, 25. How much do I have left over for my length? 50. And if area is length times width, that's 50 times 25. So my area is 1,250.